Good morning, everyone who will be seeing this video. I am Rogam Gloria, and I'm a member of Group 17. And our project for this semester is to design and implement a smart food supply chain management system for restaurants in and around Makerere University. To begin with, I would like to apologize for my video. I've really tried for it to work, but seems to not be improving or showing at all. So I'm going to allow me to collapse it a little. Now, first of all, what is this project about? This project is about finding a solution. We are trying to solve problems like demand and supply food mismatch within the cafeterias and the kiosks in Makerere University. We realize there is an overproduction of meals leading to food wastage. What does this mean? Let's say if a certain cafeteria has stocked a lot of a certain kind of meal, let's say it has stocked sausages, and in some period, for example, exam period, the number of students that are going to buy them are few because people are in and out people come into the university, sit their papers, and immediately go back to their hostels to have their meals or to read, to go through or do something as they're having their meals. So in the process, the cafeterias and kiosks are making losses during that time, and there's a lot of food wastage. Yeah, so we also see that the problem we are also trying to solve, there is also occasional stock out during peak demand. Now, let's say if during the normal semester, normal teaching period where there are no exams, and now the cafeteria has it's lacking a certain type of food that many people would like to eat. Yeah, then there is poor inventory coordination. So our system that we are trying to build for this project is to solve the above problems. We want to help both the suppliers and also the students, that the people who will be eating and feeding from these different restaurants. Yeah, so as you see, our first problem is it has come to our attention that food and drinks are prepared by vendors around Makerere University without predictive demand models. As I had explained before, someone stocks without knowing how much people actually like this food. Yeah. Then also waste-driven financial efficiency and temporal demand volatility. So we were able to synthesize data sets, and we got a data set for the cafeteria data set, for the cafeterias within Makerere University, and also for kiosks within Makerere University. And later, after synthesizing this data, we moved around to try to make sure what we actually got matches. Does it actually have a similar match with what exactly happens on ground? Yes. So these two data sets, let me rush to the model part. So first of all, one of the models we used in this project to handle our data sets was the Bayesian Network model. So first of all, to begin with, what is the Bayesian network? It is a type of machine learning model that uses probability to understand how different things in the real world are related to each other. Yeah? So you're going to think of it as a map of the cause and the effect. It's going to show you which factors affect and which factors affect other factors and by how much. Now in our data set, we are able to see, I applied this Bayesian network in the cafeteria data set, yeah? So from our data set, we are able to see that it actually makes sense that whether it is a weekend or a weekday, this affects how many students are going to come and eat. And the demand in turn also affects the revenue. So the Bayesian network draws these connections as arrows. Let's say this is how it looks like. As you see this, our picture here, that is weekend. So we were able to realize that it being a weekend affects the what? The waste level. So from this diagram, you're able to see there are 9 edges. The edges are the arrows, which means that the variable at the start of the arrow, which is the is weekend, has an influence on this waste level where the arrow is pointing, yeah? So from what I have just read about how the Bayesian network model shows, it's going to show us what affects what. So we are able to see that it being a weekend has an effect on waste level. Now from our analysis, weekends cause a high waste level because so many people are not in campus. Yeah, people are at their homes. Is weekend also affects demand. It will show whether it is actually is weekend has a low demand for food. Yeah, then we also have academic period, which affects the demand also. During exam period, the demand is going to be a little bit lower compared to continuous teaching period. Then we have the meal type affecting the cost level. Let's say if it's rice and chicken, it's going to be expensive because remember rice and chicken, first of all, the expense in also buying this meal and also affects how much you're going to sell it. Yeah. Then we also have revenue, which also affects the profit level. Yeah. So that is how our Bayesian network works. And we're able to see that parameters and the hyperparameters that were used in this model. So to begin with, what are parameters? They are the things the model learns automatically from the data. Yeah. Then for hyperparameters, they are the settings you're going to choose before training that will control how the model learns. Our parameters in this Bayesian network were the academic period. Sorry, there is a type match. Then there is the meal type. Then the waste level, the cost level, the revenue level. So you can see that how it is calculated is the academic period. Within the academic period, we have the weekend and the weekday. Yeah. And then times 1 combination, which is equal to, it's a formula. It uses a certain formula when you're obtaining these parameters, yeah? And we can also see there is the teaching, the exam, and the break. So this first one is supposed to be is weekend, which falls into weekend or weekday. Sorry for the wrong information here. Yeah, so that's how we used our parameters and hyperparameters. And we can see how the model works. It's going to count how often each combination of the value appears in the data and then converts those counts into probabilities. Yeah. So it will look at your data, look at how much waste, let's say low waste appears, finds out the probability. And we can see in our example, waste level depends on its weekend column, yeah? And it was able to obtain that 53.4% of the weekday records have low waste. Then 45.4% of weekday records have medium waste, followed by 49.8% of the weekend records had high waste. Yeah, so you can ask it questions, which is called now the inference. And it is used in our model for it to function properly. This inference method is known as the evidence-based posterior estimation, where you filter the data set to only the rows you need that match our given evidence, count how many times each value of your target variable appears in that filtered data set, giving an example of the profit level. Then you're going to convert those counts into probabilities. The result is the posterior probability distribution. Yeah. Now, next, another model we used is the Sarima model. What does Sarima stand for? Seasonal autoregressive integrated moving average. First of all, it's a counterpart of the ARIMA model. And this model explicitly models seasonal patterns in time series data. So I applied this model on the Makerere kiosk synthetic dataset, and it suited it well because the kiosk sales show strong temporal patterns. Yeah, like for example, the sales, what I mean by strong temporal patterns means that the sales, they change predictably by the day of the week. If it is a weekend, it is going to be low. If it is a weekday, it's going to be high. Then we have the academic period, teaching versus exam. Then also the hour of the day. During teaching hours, don't expect demand to be high. And then the Sarima has a model formula, which is PD, Q, then uppercase, then S, where the lowercase is for non-seasonal. The uppercase is for seasonal. The S stands for seasonal. And in this case of our project, the S is going to be equal to 7, because we are looking at 7 days in a week. This is how the model came out, where the database is the Makerere kiosk, it is pre-processed, and in this pre-processing, there is passing the data, PCA dimensionality, passing the data sets, meaning changing the data formation into a way understandable and easy to use form. Then it went through PCA dimensionality, then came in clustering, and we're able to get 3 clusters, and also ADF stationarity test. It went through, after getting the clusters, we trained and split, went through fine-tuning parameters, and then within this, it's where the model is implied. Yeah, where we have so for an easy and understanding of that model picture, we see that first the Sarima model is based on 6 components. Yeah, so we have the AR in this diagram. The AR is the autoregressive component, and it's followed by order P, the small p. Then we have the integrated, this I with the D in brackets. It makes the time series stationary by reversing it by that number of D times. Then we have moving average, which is MA, equal to, and represents the order small q. The MA component models the relationship between the current value and the past forecast errors. Then we have the seasonal AR, yeah, which stands for the small p. The seasonal AR, it works like the regular AR component, but at the seasonal lag. Yeah,